Hi ladies and gentlemen, this video describes a magnitude comparator. At first we will see about a 1 bit magnitude comparator. We will design it and we will extend that idea to a 4-bit magnitude comparator. So let me start with this presentation. The speech is organized into your learning outcomes, then a 1-bit comparator and its design. Then we will see the design of a 4-bit magnitude comparator, then the summary of your understanding. What you will learn, or you will learn to design a 1-bit comparator that will compare the bit A and B, 1 bit AN and BN, and we will extend that idea to the design of a 4-bit comparator that compares numbers AN, A3, B3, A3, A2, A1, A0, and B3, B2, B1, B0. Now let us consider the comparison between two bits AN and BN, and that N denotes a number of stage like A3, A2, A1, A0. Okay, compares with A3 and B3 or A0 and B0, comparison of 1 bit. If AN is greater than BN, it means AN is equal to 1 and BN equal to 0, because there are only two possibilities. It is a binary system. Or AN BN bar is equal to 1. Okay, CN, that is AN BN bar is equal to 1. If AN is less than BN, then AN equal to 0 and BN equal to 1, or AN bar BN is equal to 1. So now consider the negation of the statement AN greater than BN or AN less than BN. What if AN greater than BN or AN less than BN? That means AN BN bar or AN bar BN. Now consider the negation of that statement, that is AN BN bar or AN bar BN all complement. So what is a negation of the statement AN greater than BN or AN less than BN? That is AN is neither greater than BN nor less than BN, which is equal to AN equal to BN. So that is a equality. AN equal to BN is EN, that is equal to complement of AN BN bar or AN bar BN, which is nothing but A X nor AN X nor BN. Okay, so these three equations, Cn, Dn and En, I can summarize to one single magnitude comparison cell, which looks like this. These are the bits An and Bn. This is An x nor Bn. If En, what is that? If An is equal to Bn, that is if both are zeros or both are 1, then En is equal to 1. Now if Bn is greater than An, which is Dn, here this and output is high, because this is An, this is Bn complement. If Bn is greater than An, then Dn is high. If An is greater than Bn, this output is high. If An is greater than Bn, this output is high. So this works like a 1-bit magnitude comparator. This circuit works like a 1-bit magnitude comparator. Now understand this Dn, En, and Cn. This will be useful in further designs. Okay, Dn is for if Bn is greater than An, this Dn output is high. If An is equal to Bn, then this output is high. If An is greater than Bn, this Cn, this output is high. Now let us expand this design to a comparison of two 4-bit numbers. It's a 4-bit magnitude comparator. Consider the comparison of two 4-bit numbers, A3, A2, A1, A0, and B3, B2, B1, B0. So what you can do is you can make this into a QX or a sub-circuit or as a Verilog module, and you can utilize it in this the same way you used a 4-bit parallel ladder or something. Now when A equal to B, what that means is A3 equal to B3, A2 equal to B2, A1 equal to B1, and A0 equal to B0. So this implies that E, that is equal to E3 and E2 and E1 and E0. Okay, this should be high. What is this E3, E2, etc.? You have to compute with this En. Okay, I apply A3 B3 here and you get E3, apply A2 B2 here and you get E2, apply A1 B1 and you get E1, and apply A0 B0, you get E0. Then you add the 3 and the 4 of them together, E3 E2 E1 E0, and if this is a high, then the numbers are equal. A is equal to B. Now what if A is greater than B? Then there are some cases, some possibilities. If then A3 may be greater than B3, then A is greater than B. These are the numbers A3, A2, A1, A0, and B3, B2, B1, B0. If A3 is greater than B3, then A is B. Okay, A3 is greater than B. This implies that A3 B3 complement is high. Okay, That is one possibility. Or else you can have another possibility. A3 is equal to B3, but A2 is greater than B2. Okay, both should happen. If A3 equal to B3, like this is a 1 0 0 0 and this is a 1 or like this is a 1 1 1 1 and this is a 1 0 0 0. Here A3 and B3 are the same, but A2 is greater than B2. Okay, so what happens here is, what is the logic function corresponding to this? That is E3, and if A3 equal to B3, E3 is high, so E3 and A2 B2 bar, A2 B2 bar, E3 and A2 B2 bar. That is another possibility. Now I have a third possibility, that is wherein A3 is B3 is equal to B3 and A2 is equal to B2, but A1 is greater than B1. Okay, maybe this is 1 1 1 0 and this is 1 1 0 0. Okay, 1 1 1 0 and 1 1 0 0. Here A3 A1 is greater than B1. So A3 is B3 is equal to B3, A2 is equal to B2, and A1 is greater than B1. So what is the logic function corresponding to that? That is E3 E2 A1 B1 complement. E3 E2 A1 B1 complement. E3 E2 A1 B1 complement. Now, or I have a last possibility, A3 equal to B3, A2 equal to B2, and A1 equal to B1, but A0 is greater than B0. So in that case, that function, logic function is E3, E2, E3 and E2 and E1 and A0 and B0 complement. Now I can make this last statement, this item, into a logic circuit as shown here. So that thing, A greater than B output C, that A greater than B output C, the final statement that looks like, I OR them together, I put it into a logic equation, A3 B3 bar or E3 and A2 B2 bar, or E3 and E2 and A1 B1 bar, or E3 E2 E1 and A0 B0 bar. Okay. Now, what is the statement D for what is the circuit for the case A less than B? All you have to do is to interchange A and B. Okay, all you have to do is interchange A and B. If A less than B, that output D I can obtain by interchanging A and B as say D is equal to B3 A3 bar, or E3 and B2 A2 bar, and E3 and A2 and B1 and A1 bar, or E3 and E2 and E1 and B0 A0 bar. All I have to do is to interchange A and B in the equation number 2. I get equation 4D. Now the circuit is implemented as shown here. Now these are these inputs like B3, A3, B3 bar. You have to add an inverter here and make it B3, A3, B3 bar. This is a first AND output. This is A2, E3 and A2, B2 bar. This is a second output. This is E3, E2, E3, E2. Okay, E3, E2 and B1 bar A1. This is the third AND output. This is my E3, E2, E1 and A0 and B0 bar. Okay, this is E0 is not connected. E0 comes here only. So now I have these 4 AND outputs. Now along with that I add an input for C. This is C prime. C prime input along with E3, E2, E1, E0. Okay, this is also this is something additional to this equation number 2. This is for controlling this input. I give an input C prime for this one. I assume that C prime equal to 0 and E prime equal to 1. Okay, when this E prime, I keep this E prime here, A equal to B input E prime. Here what I do is E3, E2, E1, E0, they are connected to an AND gate, and I get the E output along with the E prime. I assume that E prime equal to 1 and C prime equal to 0, so that when all E3, E2, E1, E0 are high, E is high, meaning that A equal to B. When C prime equal to 0 and any of these inputs is a 1, then C is high, making that A greater than B. Now you can make a similar circuit for D with interchanging A and B in this one. This I haven't simulated. Instead I will give you it as a QX as well as a Verilog assignment. All you have to do is to add one more circuit for D and put them together, and you have a 4-bit magnitude comparator. So this I will offer you as an assignment in QX and Verilog. Probably today I will post that. Okay, now I come to the end of this. Now, what you understood is you designed a one-bit magnitude comparator with NOR circuit and OR circuit and inverter circuits. Then you designed a four-bit magnitude comparator, and that is the end of this presentation. I thank you all.